Okay, so moment of truth has arrived. We will do a parallel demo. We have provided, you don't have to clone this GitHub repository. There's actually more information on the GitHub repository. So for instance, how to run it on NVIDIA GPUs, which by the way, works also on some gaming computers. So you might try it out yourself. I produced a little flow problem. It's laminar, so no turbulence, of a setup looking like this. We have the Elmer letters here, and they are basically in 3D streamed by some fluid. I think it's olive oil I chose. Not because I like olive oil, but basically it has viscosity that prohibits to get things too turbulent. It's still a laminar flow, but still with some swirls you can see here. So it's, yeah, it produces, and I can go back. It produces nice, colorful fluid dynamics, CFD. Should we make a short break before we start, or immediately start our engines?
Maybe just to check if there are any questions, and with online participants and in-person participants, if they can access Cetonics and they are comfortable logging to the Cetonics, and everything went well. Yes, that first login. Just to. So if you have any questions online, please feel free to unmute yourself or ask them in the chat.
Yes, we'll wait a few minutes to make sure that everyone is here. So now, everyone who has still problems to get there. And did you write into the instructions to go into the Scratch directory?
Yes, they are in the GitHub link that I have shared.
Yes.
So maybe I'll share the page and just give me a second. So that's initial setup. Are you okay if I share the screen?
Sure.
Yeah. No, let's go. Sharing here. I definitely have too many tabs open.
Sorry, I should have warned you.
So the way we organized it for today is that we have placed. Give me a second. To find the proper window. This is the one. So we have placed the, so once you log into Cetonics, so these are the instructions to how to log into Cetonics with the use of the course accounts. But since there were no, I assume that everyone succeeded with that step because there were no issues reported. So the training material actually was copied to this directory. I'll increase that a little bit.
Yeah, let's show that.
So it's Scratch courses 01 Elmer parallel demo .gz, and there are some instructions here at the beginning that we ask you to go to the my Scratch directory. So there is $my Scratch, which is pointing to the Scratch directory for the course account. And once you're there, there's the copy command, and then untarring and cd into that directory, which consists of the different files, including the scripts to run the examples. And I guess you'll just.
Yeah, I take it from there. So anyone here in the room or online not at this stage, please speak up now, else I continue. First with copying. So I really start from a clean slate. And then I make this.
There is a comment in the chat. So Hui, I think you forgot to put the space between CP and the directory. That's what I can see. Please confirm if you were successful running that command. And then there should be also a space between the GZ and the last dot. So basically, yeah.
As highlighted on the screen. Good.
I'll just check with. Oh, you're checking with Quay now?
No. This someone new joined.
Okay.
So this one now post the document.
Oh, yeah, because you can't see the history.
Yeah.
Okay, let's wait for 1 or 2 minutes. Sorry for those already done.
Oh. So you are now missing the slash at the beginning of the directory. So it should be cp space slash and then space. Yep. Seems that we can go ahead.
I continue. So this is the listing now. If I go into Elmer parallel demo of the files, I will soon talk you through. The main thing we have to do, the load modules, of course, have to do is to load a certain environment, and I automatize that for you by providing a script. But that's basically how supercomputers work, because they contain a lot of software, and setting up the system for each and every software there is would basically lead into chaos. So what you do is basically you generally start from a clean slate and then add by a system which is called module the stuff what you need. So you basically go shopping, and in our case we have to tell where to shop from. That's the first line, and then have to load the modules we need for those components we will use, which is Elmer itself, but also Gmesh. You remember this is the meshing package we are going to use. So in order to execute that, you do a dot slash, and make it here, dot slash, and then load modules, and you can just type the first 3 or 4 letters and then use your tabulator to auto-complete stuff here.
May I ask, don't we need to source this, to source and then load?
You can also source it, but I guess you can just run it. Let's play safe. Okay, sorry, all back. We do a source load modules.
I think so, because otherwise it will not be imported into the
only inside the script.
only inside the script.
Yes, okay, fair enough.
So the source command with the, and I think it's also included in the GitHub repo.
It worked for me by executing, but okay.
Okay.
No worries. But maybe it worked because I had done it before. True. Yeah. So source load modules.sh. Yeah, no bad things happened, hopefully. Good things happened, because if you do a ML, it should show you those modules now being available. That means your system is set up. Short question, is the size of the font okay for everyone online and also in the room here, or should I enlarge it a little bit? Okay, good. So apparently you have better eyes than me. I can with that fortunately have it in front of me. So good. Now we are all set up for the pre-processing step. And in order to do so, we have a Gmesh input file, which is ST readable. I can just show you. You don't have to follow that step, but basically it defines your length and scales here, and then the points, and then makes the geometry. These letters. So, for instance, E, R, you name it. All you need for an Elmer mesh. You don't have to worry about the details here. Actually, it took quite long to make this mesh, but that was my problem. Generally, you spend, I would say, if everything works with the simulations, you spend 90% in preparing the data for bigger runs and more complex problems. So
I went to take a look at it as well, and I'm not quite familiar with how to get back out. What was the button you pressed to get to?
Where do you want to get back out?
I mean, you mentioned that sort of.
Okay. The less, just press a Q.
Thanks very much.
Or Control C should be also your friend in case of everything goes wrong.
I appreciate it.
Control C is the real brutal way of ending things.
Is that a non-related question if I ask what's the best practice for the MUMPS preparation that you are saying that 90% of the time of the simulation is taking for you?
If you find the answer, let me know. Well, I mean, I'm sticking here to open source software. I'm sure there are good solutions, and actually I know because I was working during my PhD for a CFD company. I think also 90% of the resources generally are put into pre-processing there. So there are certain commercial applications that make those things easier, but of course they come at a price. Yeah. So we like Gmesh. You also have, if you start more from technical applications, Salome is a nice open source kind of engineering meshing tool. So we can plug into that one. I was telling this yesterday. It very much depends on your application, to be honest. Yeah. And as I mentioned yesterday, the Elmer grid also has a interface to most common mesh formats, like from Console, Abacus, you name it. So you can check the magic numbers, as we call them, in Elmer grid. If you execute Elmer grid without any arguments, you will get a zillion of information, but the most information or most important information when it comes to formats is here in the beginning. You always have an input number and an output number, and that correspond to the particular mesh format. Like, for instance, if you want to translate an ANSYS mesh into Elmer, you would pick number 4 as the first number and then number 2 as the output number. And there is also a documentation on the FUNET V place, which I actually will display in the end of this session. Yeah. Right, so having said that, so we have the geo file, and now we are running Gmesh simply by calling it. And the good thing is Gmesh, you can either do it interactively, but also just in the shell. And it's important to put the -3 there. So because that means that it doesn't use the graphical user interface, which frankly I don't think would work from the shell here. And what we then need are these what we add is a CL scale of 0.5. I will tell you in a second what that means. And we tell it to use Elmer flow.geo as the input file. And we can give a name of the output file, which we should, because that name is important. It's hard-coded into the Elmer run scripts. We call it Elmer flow, _ CL5.msh. So what does this do? It says, Gmesh, please mesh me without a graphical user interface in all 3 dimensions, and half the scale of the corresponding mesh. That means it will, in 3D, double the amount, eightfold the amount of mesh nodes, because the original mesh is so small it would run on the PC, but it would be ridiculously small to run on the supercomputer. This will still be ridiculously too small, but it will give us something we can run on the supercomputer, splitting it into 128 parts. That still gives us a nice result and doesn't take too long. So it's chosen for that way. If you have a lot of courage, you can go down to 0.1. That would leave you with already a few million degrees of freedom and try it later. But let's stick like that. I keep that on display that everyone is absolutely sure that they have this. Is this in the document also?
It is not, but I
Is
can
it not?
update it.
Yeah. So Maciej is so nice and updates the GitHub page that if you fail to get the mesh and if you get some error message, that you can pick it up from there. I press that and I hope everything works. Yeah, looks good. I can replay the command for you if you're still typing it. While I explain, so basically it was creating us a mesh with, what is it, about 200,000 nodes and 400,000 elements. Not very big, to be honest, so you have to go much bigger to really utilize the supercomputer, but it's just for training purpose. And let's make a blocking communication point here to refer to the MPI explanations before. Asking everyone, are you there, or is there still a problem? Good. I take it as no problem. If we do a list, what we have gained now, or actually overwritten, no, we haven't overwritten because we gave a different name. We produced a mesh file, which is still in the format of Gmesh called Elmer flow CL file. Oh, sorry, I was mistyping it. We should have CL05. Sorry, online demo. You can rename that file actually you created. There is no problem with that, or you can just rerun it with 0.5 or 0.5. But it's very important that there is a 0 because else it will fail in the course. Apologies. Blame it on my chat lag. I'm rerunning it. And checking, yes, now I have the 0.5 and they are identical. So you could have just renamed that one to 0.5, but I'm removing that one now. Okay, so now we have the mesh file. Next, yes, please.
So you're not specifying any type of meshing here, just going with the default settings here, or is it going to mesh with the quadrilateral type of elements, or?
There are certain options in Gmesh, but we don't utilize that. So basically, these are, if you would talk terms in terms of them, it would be linear Lagrangian elements. So the nodes only on the corners. Okay. If you refer to that, yeah. There are options then in Elmer grid to produce something more complex, but we stay on plain linear elements in this case. Yes. But is this more or less answering your question? Okay. Good. So now we have the Gmesh file, and the next step is to make an Elmer compatible mesh out of it. And now we switch to the Elmer grid command, which I already demonstrated to you. So this is Elmer grid, and the magic numbers, you don't have to look them up, are 14 as an input of Gmesh and 2 as an output for Elmer. And then, of course, we have to tell what to take. So
three for the mesh. I think 3 was option.
It was ANSYS.
And
4 was ANSYS.
the 3 was 2 was geometry. Mesh file. Okay, mesh.
This is not the GMesh step. The GMesh step is done.
Yeah.
Now we are at the step to take the GMesh output and morph it into an Elmer readable mesh.
Okay.
So this is already a program part of the Elmer suite, Elmer grid. So if you would have an ANSYS mesh, you would give a different version number here, and then could translate an ANSYS mesh, for instance.
Based on help, it says 14 is .msh, 2 is .mesh.
Okay.
Yeah. Right, but if you have some ANSYS mesh or whatever, we can try later. That's what this session is for. Where was I? Now we need the name of the mesh we just created, which is Elmer Flow CL05, which I just insert here. Being lazy, I use my mouse, but you can just type it. And now there's something very important. We need additional flags from Elmer grid. GMesh has the feature to have quite a random numbering of its entities. So they are not in a row, they can have gaps, but Elmer really needs a consecutive numbering of all nodes, all physical surfaces, bodies, whatever, you name it. So if we would press enter now, we would get a result, but the mesh would be unreadable by Elmer. So what we have to do is to do an auto-clean on top of it. So Elmer grid 14.2, the mesh name we just created, dash auto-clean. And that's it. Let's punch it. Then there's some information, what it does. In our case, for instance, this is the inconsistent numbering. So it changed number 2 into 1, number 3 into 2, blah, blah, so on. But in the end, you get a summary that says, okay, I'm saving about 200,000 coordinates, aka nodes, into 333 elements that are the 3D elements, and the boundary elements, I think, are not accounted for here. That's why we have a discrepancy between the earlier numbers we saw in GMesh.
Yeah, it was 400,000 elements.
Can I quickly ask for a feature for auto-completion to be included in later releases?
Sorry, for what?
Auto-completion. It's hard to remember all of the, maybe that's the first time that like auto-clean or all of these dash auto-clean. If there's something like auto-completion,
I don't.
Add a feature
into Elmer grid.
just to tap.
But how would Elmer grid know what you want? Maybe you don't want to have the numbering changed.
No, in terms of the parameters only. I don't want to take the course time, but I mean, that would be nice.
Okay, I think it's very difficult because it's a compiled. It's not a script. It's really an executable.
Yeah.
So I don't think it's possible. But it's open source code. If you want to contribute to it, please do. Yeah.
I have something that I added like Python wrapper around it. So
okay, well, be my guest. Peter Rabak, I would be very happy about it.
That was my personal interest.
Okay. Yes. So that's that. If we now make a listing and, for instance, order it temporarily, you will see that there is a subdirectory Elmer_flow_CL05 now coming up in your directory. And if we take a listing of this, you will see that there is a, oops, sorry about that. There are 4 files: mesh header, mesh nodes, mesh elements, and mesh boundary, which are more or less self-explaining, right? One hint. If you, let's take a cat, then we don't have to get out of things here. If you want to check the amount of elements and nodes, you can just display the mesh header file. You don't have to do that. I'm just demoing it. So The first entry is the amount of nodes. The second entry, the amount of bulk elements, and the third entry, the amount of boundary elements. The next line is the amount of we have some AI problem here.
No, there's not.
Just a
No,
second.
it's okay. She's gone.
Was it Siri or Cortana?
We actually don't know her name.
Okay,
About the name.
whatever. So let me continue. Free means that there are 3 types of different elements following. And the code in Elmer is such that there is always the first one is the number of edges. Then the third one is the number of nodes. So this would be a triangle, 3 edges, 3 nodes. So this corresponds to a boundary element because we are in 3D. 404 would be a quadrilateral on the boundary apparently. And the bulk elements are 706, which is already a deviation from the rule I already told you, but 706 are tetrahedrals. No, sorry, no, they are not tetrahedrals, they are wedges. Yes, wedges. And they should have, 6 nodes, but do they have 7 edges? 1, 2, 3.
Yes.
Okay, no, it's not there. It sticks to the rule. Yeah. Okay. That's that. So that's one thing you can check for the size of your problem quite easily is the mesh. I presume everyone is there. If not, let me know. So what we have to do now in order to have a parallel run is to further split the current serial mesh into partitions. Okay, you remember we are sending it in our case to 128 different partitions because our one node of our system has 128 cores and each core will deal with their own, so to say, Elmer problem that are then communicating in between each other. In order to do so, we again engage with Elmer grid, but now we say we want to change an Elmer grid file, which is 2, into another Elmer grid file, namely a partitioned one, and use the name of the already created serial mesh. And now, as you perhaps remember from my presentation before, we do a part dual and a Matisse. Let's use the K-way and say, please split it into 128 parts.
You're specifying the folder name, not this mesh there.
Say it again, sorry?
You're specifying the folder name there.
Yes, it's a folder name.
So it will take all the.
Yes,
Okay.
yeah. We could actually directly go from the Gmesh file by after autoclean adding part dual and Matisse K-way.
Okay.
Yeah. But I needed the serial mesh also because we will do a serial run, then offloading to the GPU. Okay, I punch it. Lots of things happen, but basically in the end, you see that the average partition, and that should be the case. So because there's a matter of load balancing, you want to have each partition dealing with the same amount of computation needs. So you want to have, in other words, the same amount of nodes being computed in each partition is about 2,608. There is not a lot of deviation here. These are the shared ones. So they are also quite the same. So this would mean the communication is equally distributed. Let's go upward. Oh, no, sorry, the amount of nodes and the shared ones are these, sorry. So the shared ones are then, well, there is a slight imbalance, you see. So for instance, number 7 has 68 shared nodes, where the number 6 has 292. Why is that the case? Well, generally the problem is that you have confined entities. So you have boundaries to the outside world which don't have to communicate with something else. So by geometric conditions, you will have partitions that have lesser interface with others, simply because it's a confined body. If you would have periodic conditions, for instance, you could avoid that. You can have perfect distribution of shared nodes.
I have a question. So for this second command with Elmer grid, we don't need to use the auto clean anymore, right?
No,
we
because
already
it
cleaned
has
it.
been
Yeah.
cleaned.
Okay.
Yes, yeah. Good question, though.
Sorry, can you
Um,
display the command again?
Yeah, sure, for sure. Hold on.
And also for everyone, I am constantly updating the GitHub page, so you have all the commands there as well. So if you're late with executing those things, then it's up there.
It's a big question. What happens if we add the auto clean like again here? I'm trying to break the code.
Try it. It's a free world.
Okay.
No, bad things will happen. No. I think you'll be fine, actually, because it will check, okay, is there something to clean? No, there's nothing to clean.
But I didn't put the number of the node. It was smart enough to say one argument is missing, and then I'm trying to put extra stuff to see what massive.
Yeah.
Was the same. Nothing happened.
Nothing happened.
No.
That
What maybe happened?
So what
From
did you
here,
do?
that's the beginning.
Yeah.
And then I didn't put that argument. It was asking
My theory should be.
this is
Sorry, that sounds
and I didn't put one.
Yeah, okay,
So
because
what-
partitioning without telling and how much partitions you want to have it.
I think it's.
I think
that's
that's
not
what
the
this
case.
means.
That's
Do you
the
see
one.
any difference?
No, I wouldn't
No.
expect anything because there's nothing to clean.
Our first question.
It already is, everything is in consecutive order. So,
And doesn't say to me, we need to message that auto clean is not needed.
well, it did it. It came across the fact it's nothing to clean.
Yeah.
So we step up.
Good. Everyone there?
Yes, I just have one question. In the output of that previous thing, it had the sort of the average total sections down the bottom. It has all of that 0 at the bottom right, but with seemingly no header above it. Is that the average error count or?
Oh, no, you got me on the wrong foot here. Yes, there's a. I have no idea where these zeros come from.
Fair enough.
I can ask Peter Ravak, my colleague. He's writing that code and maintaining it. No idea. But there is also some other statistics, as you can see. For instance, the maximum partition sharing. So you can have nodes sitting on boundaries of several partitions. You want to also minimize that because the communication then for this node is quite heavy. So the maximum, I would say, partition coordination number of a single node anywhere in the mesh is 4. So one node can at maximum be part of 4 partitions if it's on the boundary of those. This might also be an interesting number. Yeah, there's a lot of information there, but if we start digging into that, we sit here tomorrow. Okay, good. I think that's the point in time where the truth comes if things still work. If we tested this morning, so everything was working. So we will submit our first run. And I don't know, Maciej, so should we discuss the run script a little bit, perhaps?
We can. Do you want me to do that?
If you prefer to do it, yes. It's your system, so I think actually it would be a good idea to do
So
so.
are we starting with the CPU version?
Yes, we do the CPU. I guess you should switch
Yep.
the screen.
So stop sharing this. Go. Should be able to hopefully see. Okay. So I think what we want to see is Elmer. So we will be starting with running this script, or actually open it slightly differently. Okay, so it starts with some of you might be familiar on how to submit a job to Cetonix, but if you're not, before you submit a job, you must specify the resources your job will be using. So this first part of the script is actually specifying the resources. So going from the top, those lines that start with sbatch, so hash sbatch, are defining some specifics about your job. So both on the resources side or for instance, the name of the job. So starting from the top, we are saying to the queuing system, so the Slurm, that the job will be running maximum 20 minutes. Then we are saying that the job name for this specific job will be Elmer CPU. And then we are defining how the output and error, standard output and standard error files should be called. And this is basically a syntax here that is using the name of the job and then .out or that .err for the error and output.
Plus, if I may add, the J, I think is the job number. So if you have multiple instances of that run, you can identify the instance with of the output file with that number.
So it's the name of the job followed by underscore followed by the job number and then the out or error. Now, for your job, you always need to define an account under which you will be running. Account might be seen as an equivalent of the project at Pawsey. So this is basically an identifier of your project. Here we are using the courses project with courses accounts. But if you have an allocation at Pawsey on Cetonix, then this will be usually a code starting with Pawsey and then a five-digit number. Then for this course, we also have the reservation on the system. So this line just defines which reservation we want to use.
Just one comment. There is still, because I think we had it commented out. Now it's not commented out. You need the trailing.
Yeah.
Sorry, the hashtag in the front.
Yeah.
So don't follow those instructions in the comment.
So don't remove the hashtag here.
Yeah. So leave it like it is.
And then the following instructions for Slurm will tell Slurm how much resources in terms of compute resources needs to be allocated to the job. So what we are saying here is that we want to use a single node, so nodes equal to 1. We want to use 128 tasks per node. So because a single node on Cetonix has 2 CPUs, each of these CPUs, so AMD Milan CPUs has 64 cores. So altogether you have 128 cores available within a single node, right? So we are using all the available cores to run 128 processes, which will be using those partitions that we have just created with the Elmer grid command. And this line is commented out. It was not needed for this run. And then we also say sbatch exclusive. Exclusive means that you will be the only user of the node. So there will be no other jobs that will be running on that specific node. There are certain scenarios and certain workflows that are being run on Cetonix where researchers decide to use only a fraction of the node, then this can be left out, and then you can use, for instance, 2 cores or 5 cores out of the nodes. Whereas here we want to demonstrate the full power of a single node, and we want to use all the MPI processes available there. So we basically make sure that we use an exclusive mode. And other commands that are here are defining how to load the module. So Elmer module, this is actually something which is very similar to what you find on this load environment script. But we are also saying that the run will be not using any multi-threading. So Elmer also have the possibility to run threads within a single so OpenMP threads within a single MPI process. But in this case, we are planning to use 128 processes and no OpenMP threads within that run. And then we simply run the solver with the srun command. So srun command basically allows you to run an executable on the system. And thanks to all those settings that we did within the Slurm job, it will identify that it should be running on 128 processes and execute the Elmer solver binary.
Yes.
Are there any questions to that?
Well, having other jobs on the same node, saying about the blocking OpenMP stuff, that would affect a bit reproducibility, right? Because it would change the ordering of processes.
No, I don't think so. So the resources are allocated,
Mm.
and they are your resources, so it's your user space. So I don't think that it should not. If it has an influence on your MPI, depending whether you have shared resources or not, you should call us because then there's a problem in the code. Or you call them because there's a problem in the allocation process. Yeah.
So that's I mean, different systems will have it configured in a different way, but in the case of Cetonix, when you ask only for a fraction of the node in terms of the number of processes or cores, then you will be also allocated with a equivalent of the memory as your own memory space that no one else can use as well. So that's basically, let's say if you use only two, so each node in the work partition on Cetonix has 256 gigabytes of memory. So if you only use two cores from the node, then you use a fraction of that. So 128 cores divided by 2, so 64. So a fraction, 1/64 fraction of 256.
Okay. Yeah. No.
But probably is referring to the point where he was discussing about the blocking and non-blocking communications. So the style of programming within the code, how you want to do it. I was trying to explain that. So once you have the code, you can't do anything with when you try to run something on that.
It's anyhow compiled.
Yeah.
Yeah.
But in general, Slurm, so the queuing system that we are using, should take care of making sure that no one else is using the resources. Of course, there might be some bugs in the software that might do some memory leak or stuff like that.
Bugs.
There are no bugs in software. But in general, if you have a proper schedule, it should take care that your resources are protected for your specific job. So no one else should be going in the way of your your run. There are also scenarios where you can run on a single node using, let's say, 2 cores, but allocating the entire memory of the core of the node. So this is also possible.
Right. So I guess switching back here. Thank you. So next step is then to submit that job script. And you do that simply by sbatch command, run Elmer, CPU, MPI, sh. And then it will say it's submitted. And if you take a look at the listing, you will at some stage see some output files popping up. And if you're fast enough, which I don't think I am at the moment, you could make a tail -f and then insert that file. Oh yeah, we still were fast enough. So basically it fills that file as it runs. And it doesn't really take long because it's a very small case. So, but by intention, it was chosen like that. But you see the convergence history, so it always reaches 10 to -8, and then says I'm good for that time step, and goes to the next time step. Don't worry about that. That's a gray typical thing. Nobody could find a solution how to get rid of these warnings, but ignore them. So everything is good. But it's annoying because it fills half of your file in the end, and it's very hard to find the place where it stopped. which I try to do now. Scrolling up. Yes, because and there's also something that comes from each and every node, so the order is very randomness. But you will find in the end some summary how much time has been spent on CPUs and wall clock time. So basically, if you subtract those two, you see the time then that the system was wasting by being idle. But they are quite similar. So our run took 37.48 seconds wall clock time. Okay. If you would do it serial, it should be about 128 times longer. We can try that later, perhaps, but that's why we do parallel computation. Good. Now we have a sequence of only 20. If you want to, you can change that in the Elmer file to get a little bit of a longer sequence. Maybe I do that immediately and we can rerun it. In order to do that, let's open the file. And the file is called Elmer Flow GCR. That's for the CPU run. I don't go into details here, but you can increase the number of time step intervals to be computed, for instance, to 50. Then there will be a nicer sequence of things to be watched and just save it. Now I think we might have a problem if people are not able to use editors. I don't know, maybe is everyone online able to change a file on the system? If not, please speak up. We have to give you instructions on how to do that. There are different ways to do it. So I'm using Emacs, other people using VI, but basically they are all ASCII shell-based editors. If not, if things are too complicated, we just leave it at the 20 and we can do the post-processing then. But I will do a run with 50 time steps. I'm just resubmitting things here. And let's see if something comes up. Yes, so we can do a tail as F. If you're not able to deal with the editing of files on Cetonix, don't worry. You're good with 20 time steps also for the testing of the post-processing.